Okay, today we will do not separable, exact equations. Now, to understand what exact differential equations are, you want to review this thing called implicit differentiation in Calculus 1. It's been a while you've seen it, so let me show you how it's done. So suppose you have something like x squared y plus 5xy squared plus 3y cubed equal to 0. Suppose you had this. And you're told to find y prime implicitly. Then you solve such questions in Calculus 1 by using appropriate chain rule or product rule as you need. So all you have to do was just differentiate everywhere with knowing that y is a function of x. You have to keep that in mind. Okay, y is a function of x. So when you differentiate everything, here's x squared is a function of x, and y is again some function of x. Therefore, when you're differentiating this, you need to use the product rule, where you differentiate the second plus differentiate the first. Y. Again, the same thing applies here. You differentiate the second, and then plus differentiate the first. 5x, if you differentiate it, it's just 5 by itself. And then for this one, see, it's a nested function because y is a function of x nested inside y cubed. So when you differentiate this, you have to use the chain rule, which says you differentiate this as if it's a function of y. So 3 comes down, so it's 9y squared y prime. So it's 9y squared, but then the inside function, which was y, has to be pulled out and you have to differentiate. That's what chain rule says. So you have to take the inside function out and differentiate. And that's equal to 0. You're almost done, except over here, how should you differentiate y squared? What would you get? 2y y prime, because see, this prime here really means you're differentiating by y prime, differentiating by x. Sorry. This prime really means you're differentiating by x, and since you're differentiating y squared by x, and y is a function of x, you should really try to differentiate this as the chain rule, where you differentiate this, you get 2y, but the inside function, which is y, has to be pulled out, and you have to put y prime on it. You have to attach that, right? So that again gives you x squared y prime plus 2xy plus 2y. You can 2 times 5 is 10. 10x y prime. And then plus 5y squared plus 9y squared y prime equal to 0. And then the next step you're supposed to do is you solve this for y prime, because you're trying to get what y prime is. So you gather all the ones with y prime together. The ones that do not have y prime, you move to the other side. Factor out the y prime, you divide, and that's what you get. Okay, that was the answer that you would put when you're doing calculus 1 implicit differentiation. Okay. Yes?
What about the 5y squared?
This 5y squared was created because I was using product rule, right? And this one was created by differentiating 5x. So that gave me 5. So that's all you have. All right, but I want you to stop right here. Instead of moving forward to get what y prime is, I want you to just stop right here and look at what we have here. What do we have? Don't we have a differential equation? You don't think so? It's a differential equation, isn't it? I see an equation. I see a derivative. Differential equation. Right? So here's another way to think about the following question. You can just turn the tables around and ask the following question. Suppose you're given this. Can you find the original equation where it was originally differentiated from? That's exactly, that should be exactly this. Well, actually, if you try to integrate, there's always this integration constant, so you would want, when you integrate this, you would want this equal to a constant. Okay. So calculus 1 goes this way. You're given some relationship between x and y, and you differentiate, you get something, and then you solve for y prime. Differential equations goes the opposite way. It gives you some strange equation like this and says, can you find the original equation, what it was? Okay. And such type of questions are called exact. Not all equations are exact. Only some classes of first order differential equations are exact. I'm going to tell you later how to identify those which are exact. Okay? But let's try to see how we can come up with the following. Right? Now, let's just stop this for a moment and think about what this business is about in general. In general, you have the following relation. You have some function that has x and y in it equal to 0. That's what you're given. Just like here, you're given some function equal to 0. Okay? And then, in order to get to this point, you have to do the differentiation implicitly, right? You have to do the differentiation implicitly. And it works like, well, you can think of the derivative of this in the following way. You have the function f, which depends on x and y, but you're also considering y as a function of x, right? That's what we're doing whenever I try to differentiate implicitly, right? So I have a relation which is given by some strange function, and when I have this equal to 0, I'm implicitly saying that y is a function of x, implicitly. Right? Now, in such a case, we can actually use the calculus 3 chain rule to solve calculus 1 implicit differentiation. So let's see how that works. Okay. So first of all, if you want differentiation of f with respect to x, if you see, what is implicit differentiation? You just differentiate both sides. The right side is 0, so we don't care. We just have to differentiate the left side with respect to x. What is this? So let's think about what that is. According to this chain rule, there are two ways that change of x will change the value of f. First, you may find how much f changes when you change x by itself. But there's another way that change of x could bring the change in f. That's when f changes with respect to y, and then y also changes when you change x. That's the chain rule, right? That's the chain rule you learned in calculus 2. So because the left side is exactly this, we see that once you take this and you differentiate, you end up with the following form. You get f differentiated by x, partial derivative with respect to x, plus f differentiated by y times y prime equal to 0. And you can basically think of this as a shortcut for solving implicit differentiation questions. You can actually solve this for y prime. Let's see, you move the fx to the other side, and you divide by fy. And this cute little formula will solve any implicit differentiation question that you are given in Calculus 1. I know some of you like to go back to Calculus 1 and retake that just so that you can improve your GPA when you graduate. This is a wonderful formula to use when you get back to Calc 1 in case you want to take that class again. I wish I could have time to show you the power of this formula. It makes everything so easy. All right, but anyways, once you get this theory, once you have this theory, let's try to think about. So this is implicit differentiation. Now let's think about solving exact differential equations. Now exact differential equations, they look like the following. You have some function some differential equation given in this form. And from here, we're trying to find out what f was. What is f? What was the original f? That's the way you understand this exact differential equation. Okay. Oh. Okay, now let's come up with our first example. Example 1. Solve x squared y prime plus, I'm just copying this one, 2xy plus 10xy y prime 5y squared plus 9y squared y prime equal to 0. So here's the differential equation that we are about to solve. Over here, it looks like I just explained things without really giving you any conclusion, but somehow this way of looking at this problem is the key to solving this equation. Now, how do we do this? Well, see, this calculation tells us that whenever you have an exact differential equation, it will always have terms that contain y prime and the terms that do not have y prime in there. Okay? So I see y prime here, y prime here, y prime there, right? And these do not have y primes in there, so I'm going to put 2xy. Solution. First, I'm going to rewrite it as 2xy plus 5y squared plus x squared plus 10xy plus 9y squared y prime. So I just wrote this equation in this format because if you write it in this way, then the question is clear. I have a single function whose partial with respect to x is this function, whose partial with respect to y is this other function. What was the original function? That's the question. Actually, we've solved questions like that in Calculus 3, multivariable calculus. Do you remember? When did we do such a thing? Nobody remembers. Somewhere is too long. All right, we learned that when we were trying to find the potential function of a gradient vector field. So if we are given some vector field, then if we knew that it was an exact vector field, then we could find the potential function, right? So that's exactly what we're doing here. All right. But it's okay if you forgot that, okay? Let's try to tackle this question now. Now, what is this thing again? That's f differentiated by x, isn't it? So how do you recover your original function? By taking this and integrate by what? If this is obtained by doing a partial differentiation with respect to x, to recover your f, what should you do? Integrate by x. So you get x squared y, 5y squared x, and then plus some function of y. Now, instead of plus c, I'm putting a function of y. Why is that?
Because it's implicit.
No, because this is, you're undoing the partial derivative, right? If you did the partial differentiation with respect to x, this will give you 2xy, this will give you 5y squared. What would this happen if you did the partial derivative with respect to x? 0. Because any function of y is considered as 0 when you do the partial differentiation. Now, any function of y is considered as a constant when you do the partial differentiation, right? So this is what you get. Now let's look at another view of f. For this second one, this is f partial with respect to y. So in order to recover your f, what should you do? Integrate by y. If you integrate by y, this will be x squared y. X squared integrated by y will be x squared y. Y integrates to 1/2 y squared, but half of 10 is 5. And then y squared, if you integrate, is y cubed over 3. And 9 divided by 3 is 3y cubed. And plus another function of x. And note that this is a description of the same function. I have a single function described this way, and another says it's describing this way, with these two unknown. I don't know what goes in here. It's just, the only thing I know is that this is some function of y, this could be any function of x. Okay. What should this be if these two are to be the same?
3y cubed.
This one must be 3y cubed, right? Then these two are the same. How about g of x?
0.
0. There's nothing that has that's x of any function here, right? So this I can just set as 0, and this I can set as 3y cubed. Then I can harmonize these two descriptions of the function as a single function. F equals to x squared y plus 5xy squared plus 3y cubed. This is a harmonization of the two different descriptions. And therefore, the answer, the final answer is x squared y plus 5xy squared plus 3y cubed equal to 0. Usually, oh no, it's not equal to 0. What should I do? Should be a constant, right? Why is that? Because if I integrate the right side, I'm integrating 0, so it gives you a constant. Okay? So the left side, if I integrate, I get this. The right side, if I integrate, I get C. And that's the final answer. Okay. Yes?
The y prime, does that just, like how it's like x
Oh,
squared?
no.
plus-
Okay. So I see your question. Okay.
Yeah.
So the question you're asking is, I had a y prime here. Where did it go here?
Yeah.
Where did it go? Well, I'm saying that this thing in front of y prime is fy, because that was our calculation. So fy was this thing, and fx was this thing. And y prime is this y prime. Okay? So that's why this is fy. I'm integrating by y to get that. Okay. And so I get this answer. Notice that it's not possible to solve for y. This is a cubic equation, so I mean, if you use Wolfram alpha or something to find the solution in terms of y, it's just horrible. It's better to leave it like this, okay? So when your differential equation is exact, I still haven't told you how to identify whether an equation is exact or not. Somehow, because we know that this originated from an implicit differentiation, we know that it's exact. But suppose that you know you have an exact differential equation. Then you can undo the implicit differentiation this way to find the original like this with some constant which cannot be determined. And this final thing you can't solve for y. Usually for the first order linear or separable, you always solve for y to put it as the answer, right? Here, it's often the case that you can't solve for y. Some very special cases you can. In that case, it's ideal to solve for y, but in most cases, it's much more simpler to leave it like this, okay? Now, let's see if we did get the correct answer. This is what we had. Where did we start? This was where we started, right? They're the exact same thing, right? So, exact differential equation is something that is in the opposite direction of an implicit differentiation. Okay? Because whenever you do an implicit differentiation, you end up with some kind of a differential equation. There should be a class of differential equation which originates from such a thing, so you can just go backwards to find this, and the method is something that I explained. Okay? I'm going to streamline this approach and everything again, but I just wanted to give you some idea of where this exact differential equation comes from. Okay? You have any questions?